Welcome to the 820. Why 820? Well, it takes about 8 minutes and 20 seconds for light to reach us here on Earth, and we're interested in photonics and light. Today's episode is patent 4875006 from Photon Dynamics. This patent is based on technology I first saw at the International Test Conference in 1988. It was submitted in 1987, and there's a paper from IEEE you can download discussing how the circuitry works, how the thing works, but that's protected and I'm cheap. I didn't buy licensing for that paper, so I looked at the patents and that's public domain. I went down the rabbit hole a little bit on this. There's 3 patents it references which are kind of similar, and the dates are around the same time. They're all about 20 years old and therefore in the public domain. This patent demonstrated using a laser to time electrical signals going out to a device, and then it uses that same laser to compare voltages coming back from the device. And this is based on another patent, but it was the first time that I had seen optical light being used to both create voltages signals and receive them. I'm sure it was done before, you can see in the earlier patents, but this was like a big thing for me. So Photon Dynamics was founded in 1986, and their primary business is flat panel displays. So my belief is that they made most of their money selling industrial equipment that tested LCD displays or flat panel displays, and I believe that's what their primary equipment does. From what I understand of the patent, the issue with this system was essentially that although you were able to generate very fine pulses and measure very fast signals, the 76 megahertz repetition rate meant that you could only take a snapshot in time and look at things 76 million times a second, and that wasn't enough. I think that was the root problem here, but and that may still be the problem with certain applications of photonics. But since 1988, there have been a lot of advancements. This image is figure 6 from the patent, and this is the key of this entire episode. On the left, we have a light source. That's the YAG laser, a very expensive laser, which 40 years ago was, a precious commodity. And now we know we can get lasers for 60 cents each. I don't know if we can get pulse lasers at 60 cents each, which is what they were doing. But again, 40 years now, lasers are cheap. Then we run it into a polarizer, and so we have to learn about polarization. I've been learning on that, which then polarizes the light, I don't know, vertically or horizontally, and then or maybe even circular. And then there's a quarter wave plate. I don't know what that does. Maybe I have to look at the description some more. But essentially what we have, that dotted line, is a light beam from the laser, and we have circularly polarized light going in. So if you just think of a circle, and the light is going through this magic electrical optical crystal, which is the heart of this magic patent. And they're using either it's Optical, they call this thing Optical cell. And what's happening here is they send a circle, if you will, through this crystal, and the voltage across the crystal squeezes that circle in one direction or another, proportional to the voltage. And we can detect that squeeze without all the bandwidth issues of using lots of copper and lots of electrical things. So then that light is actually shifted by the voltage, and the voltage the bandwidth of the voltage signals we can detect are in the hundreds of megahertz. Then we go to a special prism that separates the X and Y component. Straight out the right is the X component of the squeezed oval, and going straight out the bottom is the Y component of the squeezed oval. These are picked up by gallium arsenide photodetectors. So these are high-speed light to voltage diodes that will convert the amount of light each sees into a voltage. And then this voltage is sent to an amplifier that expands the delta between these two and converts it to a voltage. And that, my friends, is the heart of this patent. The key to this electrical optical crystal is that, let's assume we have all photonic computers where everything's in light, but we don't need electrons. But for a while, we're going to have some things that are all light and some things that are electrical. We will need these electrical optical crystals to manage that. And today, right now, the key development in electrical optical crystals is in high-speed networking transceivers. On a Google search, you can find inexpensive transceivers today from $16 to $40 each. On the high end, you can pay as much as $31,000 or possibly more for a 400 gigabit transceiver today at the time this was made. And that's the money that's driving most photonics research today. So if you're looking for stocks or any kind of investment opportunities, this is where the money is right now, because that's where the technology is. If you do a search for optical transceivers, you'll get a bunch of hits of things that maybe aren't transceivers. In this case, Keysight is a company that makes test equipment, and T24 gigabit is the next big thing there. This link was a hit that came up. So Intel makes FPGAs, which are called field programmable gate arrays, and those are customizable circuits. Like, you can think of them as erector sets of logic. And so Intel has a foot in the ground here with a PAM4 ASIC line that is going to be the base connectivity between your optical transceiver and the electrical world. Another hit that came up was an article on 5G connectors. Molex is a connector company. They've been in the industry for decades, and they're addressing some of the needs of getting all these lower speed connections in a high enough density to go high speed optical. Paper was on lasers and high speed, and I kind of glanced at it. Its basic take was in data centers. I think data centers using a big chunk of the world's energy. I think 10% of the world's energy consumption now is data centers. And so data centers need to transmit data very quickly, requires high-speed lasers that can transmit data for over several kilometers. For photonics, on a desktop computer per se, you don't need to transmit light that powerful. You only need to go a couple of feet, right? So that article's maybe not necessarily going to tell you how to get to an optical computer, but that's where the money is today. The data centers need high-speed communication, and they're connecting these boxes, these electronic boxes that are not photonics, with fiber optic cable right now, and that's the state of the art today. One of the things I may talk about in future episodes is PAM4, PAM8, PAM6. These are digital techniques on the electric side to up the bandwidth, or basically increase the amount of information you send in a unit of time. Thanks for listening. Have a great week.